Okay, hi again, everyone. Good morning. I hope you've had a nice break last night from Fortran. Of course, we're back at it again today. Hopefully, we'll make some nice progress, learn some cool new things that can really help you, start to make functional bits of software using Fortran. Some people haven't yet joined us, but I mean, this is being recorded. It'll be available on YouTube, so they can catch up that way, or I can help them if they need any help with anything particular. Of course, you can all go back to the recordings as well if you want to, and the material itself. I'll just put another link to the material in chat in case anyone lost it from yesterday for whatever reason. So you can open it again in your own browsers and follow along. Yes, this morning we're just going to start exactly where we finished yesterday on the next section, which was going to be array expressions. So let me just start sharing that. Okay, there we go. So the last section that we did yesterday was on using arrays, array declarations, and we worked through this material, saw how we could use the dimension attribute when declaring a variable to make it an array of whichever rank we like. Here we have a rank 2 array of size, so of shape 2, 3. We went through that. We saw how we could also create allocatable arrays where we defer their creation until after they've been declared, until we know what size we actually need them to be, at which point we then use the allocate intrinsic function to say we want them to be this big, and later on we can deallocate them to free that memory again. And we finished off by looking at this little exercise here. We walked through that on how to change that code to calculate pi through a set of iterations to use arrays, so that it can store these quantities along the way. And then at the very end, we just saw how to change it so that it works until pi has converged. It loops until pi has converged, then tells you how many iterations it's taken and leaves. That wasn't so much about arrays, but it could be handy just to see that being done. But yes, this is where we are now for this morning, array expressions and assignments. So this is, I think, where Fortran's power with arrays really comes through, because Fortran makes working with arrays very, very easy. It really sort of gets the language out of your way and just lets you do things with arrays. It makes it a very comparatively pleasant experience, I guess, compared to some situations where, in other languages, where you really find yourselves wrestling with arrays, and Fortran just provides the syntax for you to do that. So starting with this, the first thing that we really need to think about is how do we talk about sections of arrays. So we call this an array section, and it uses syntax that's perhaps a little bit deceptively familiar, actually, to when we were declaring arrays. If you remembered, when we declare an array, we can choose the lower and upper bounds by putting a colon in them, by choosing the indices. Remember, Fortran starts indexing at 1, a little bit different from a lot of languages which start indexing at 0. But we can manually override that and say to Fortran, no, we want the indexing to start at whatever we want, just any integer value. And then we can set what the upper index was by putting a colon between the two. So start index colon upper index. An array section looks kind of similar to that, in that it lets us talk about some subset of an array, some subsection, if you like, as well, with colons. And to do that, you have three optional components. The only thing that isn't optional is a single colon. The first thing you say is the subscript that you're going to start your section at. Then the subscript or the index equivalently, it means the same thing here. The subscript or index that you want to finish your array section at. And then optionally, you can give it a second colon and a stride. In practice, what does that look like? It means that if you have an array called A, which is rank 1, you can talk about the whole array by just talking about it with just the letter A and no brackets, no colons. So if you write code and you just put the letter A in there, you're instantly talking about the entire array. You can also add brackets, colon, bracket. So this is using the only non-optional part of an array section, the single colon here. We've put that in the brackets here. We're now talking about the whole array again. So if you give it a colon without any other information, you're talking about everything in that dimension. We'll see an example. Don't worry, if this is a little bit unclear, we'll see some examples of this. That's very, very helpful that the university laptop keeps asking me to update in the middle of this. Next, you can talk about something a little bit more interesting here. Here we're talking about A, but only the elements 1, 2, 3, and 4. And we do that by just doing 1 colon 4. We can do just colon 4, and that means everything up to and including 4. So if we began at 1, we just have 1, 2, 3, 4 again. If we had -5, it would be starting at -5 and running up to 4. Whatever the lower bound of A is, it will start at that point and go up to this value which we've given it, 4. Then we can introduce a stride as well. So A2 colon colon 2. So this means this is a little bit unusual looking, perhaps, if you're not familiar with this sort of thing at first. This is saying start at 2, and then because we haven't given it an upper limit to the, so there isn't a value between these two colons, we're saying just go on until the end. So we aren't setting an upper limit, just carry on as far as you can in the array, but go with a stride of 2. So start at 2, carry on to the end with a stride of 2. So 2, 4, 6, 8, 10, up as far as it can go. It does work fairly similarly in NumPy. If you use NumPy, if you do array broadcasting there, you can get something that looks similar with that. So that could be a familiar point of reference. Oh, and a question. Can you put something like end between the colons to mean the same as 2 colon colon 2? Will that upset? Yeah, that's upset it. I mean, if you know or have a variable saying what the upper limit is, you can use that, or just put the value in hard coded. If it's going to be a constant number, just put in the literal. But I think this is fairly flexible. This should be fairly obvious. Once you get used to it, this is pretty obvious. This is saying start at 2, just carry on as far as you can until you reach the end, but use a stride of 2. So yeah, so you could only use end or something like end if it were a variable or a parameter that had the correct value in it, but there's no actual keyword in the language to represent that as well. I hope that answers the question. Brilliant, thank you. Okay, we'll go through a little bit more and then we'll see. I think yes, we have some examples down here that will show that a little bit more clearly, perhaps. So why is this useful? It's because it lets us do array maths very quickly without having to do things like loops. It makes it very, very simple. We can compress a lot of array operations into single lines of code. So let's imagine we've got two arrays, A1 and A2, excuse me, which have a shape of 4, 8, and then another array called B1 with a shape of 4. They're both integers. We can immediately just do things like this. A1 equals 0. Because we haven't provided any slice information and any array section here, we're just talking about the entire array. So this A1 is talking about the entirety of A1, all 4 by 8 elements equals 0. Then we can do A2 equals A1 plus 1. And this just takes all elements of A1, element-wise adds 1 to them, and stores that in A2. Then we can take A1 and say we'll take the original elements in A1, multiply them all element-wise by 2, so just double every number inside A1 and store them. Then using an array section, we can say B1 equals A1, and we're taking the section colon, comma, 1. And this means that we're taking, well, here it says B1 set to the first column of A1. If you do want to imagine the arrays in rows and columns, this means that because we've put the colon here, we're taking all rows and the first column, and we're storing that in A1. And you should be able to see that that then matches the shape between the two. So when you do these things, when you have an array on the right and an array on the left of your equals sign, they have to do what we say, and they have to conform. That is, the shapes have to match. So whatever's here has to have the shape, the same shape as whatever's here. And in this case, that is true. B1, A1 colon, comma 1 has the same shape as B1 because B1 has a shape of just 4. When we do colon, comma 1, we're saying do all of this, so all of the 4, and just a single one of those 8. And that's the same thing as just having a shape of 4. So this is just equal. This, once it's gone through this array section operation, is just an array of shape 4, a rank 1 array of shape 4 to be completely clear. So if they aren't the same shape, you can expect, if it's a statically allocated array like this, then you can expect a compile time error, hopefully if the compiler is doing a good enough job, or else a runtime error if it's an allocatable array. So the one that wouldn't make sense is this: B1 equals A1. B1 has a shape of 4, A1 has a shape of 4, 8. This is not the same thing as this. The compiler cannot interpret how to compile this. It doesn't understand because it doesn't make sense. Hopefully it doesn't make sense to all of you. How can we say that 8 times 4, so there are 32 elements here in a rank 2 shape. How can we fit those into 4 integers in rank 1? It can't be done. It just doesn't make any sense. So moving on to a quick challenge. So there's a little bit of sort of coding style that we're talking about here, I guess. How do we interpret the following two assignments? D equals 1.0 and E with an array section meaning everything in a single dimension equals 1.0. Compile example 1, check the errors and improve. So let's take a look. So here I am logged into ARCHER2 again. And if I cd into the directory, oops, it's episodes, files, and we are now in this one, 06. And example one is what we're looking at. So let's just take a quick look at example one before we try to compile it. We're creating those same three arrays, A1, A2, and B1. We're doing the same things that we saw just now, setting them equals to various things, and then we're going to print them. B1 is B1. Set B1 to the first half of the first row of A2. Okay, so let's just take a look at what's happening. So I should have the Cray compiler loaded because I've just logged in, and the Cray compiler is the one that we use by default. And we get some errors. Okay. And thankfully, it's fairly helpful here. The first thing that we see is assignment of a rank 2 expression to a rank 1 variable is not allowed. Okay. We saw this happening. B1 equals A1 doesn't make sense, so we need to fix that. But then we've got a second assignment, B1 1 to 4 equals A2 1 4 to 4. They are not conformable. It's telling us in fairly helpful language here actually that the left and right hand sides, left and right, do not conform. They aren't the same shape. So let's quickly go back into that code and try to fix that. Set B1 to the first column of A1. So it didn't like this. So we can see that it's doing the wrong thing. B1 equals A1. They're different shapes. So let's make it the first column of A1. That means we want everything in the first dimension, which if you want to think about, again, I'm not sure it's always a good idea, but here we're doing it, saying that the first dimension are rows and the second are columns. That's the mathematical way, I guess, of thinking about indices. So here we're really enforcing through our language that we're thinking of these arrays as vectors and matrices. But this would be doing the equivalent of that. If we're really thinking about them as vectors and matrices, that's what we've done there. B1 is now equal to the first column of A1. Let's just quickly check that that compiles. It does. Let's fix that second issue where B1 1 to 4 equals this. So set B1 to the first half of the first row of A2. So we know that we want this to work. So this is saying the first row. This A21 is the first row. Hopefully it's fairly obvious what's gone wrong here. Here we're saying 4 to 4. If we do an array section like this, 4 to 4, this is just the same thing as that. Array 1, 4. We're saying start and end at 4 is the same thing as just saying indexed 4. So the problem is that we've got the start and end indices the same. And if we want to make it just the first half of the first row of A2, we just need to have it start at 1 rather than 4. And now you should be able to see, because we've just got a single row here and 4 elements there from that row, we can put those into B1. And if we compile that and run that, that should work fine. Oh, here's where the interesting. So this is Cray. This is the Cray compiler trying to compress output, trying to save space. So I'll just show you what that looks like if you build this with GCC instead with Fortran. That's a bit more helpful. So you can see this is what the Cray formatting is doing. It's saying B1 is 4 lots of 2 because it's printing out 4 2s. B1 is 4 1s. And Fortran is actually printing those out. I prefer this. I think that this saves space, but is a little bit unintuitive, I think. It certainly has its advantages, but I just find this a little bit easier to read. There's nothing wrong. This is just what the people writing the compilers decided to do. These standards gives them that leeway, and they've made their different choices. One thing I do want to just point out, I think we do possibly mention it later on, but I'm just going to talk about it here. Is you might sometimes want to be a little bit careful when you're writing code like this. You can imagine if this is very long, this is a very long lot of code, and we can't see this. This is hidden thousands of lines, perhaps, if it's a really big chunk of code, thousands of lines above, and we're just getting to this point, and we see A1 equals zero. If you aren't careful, this can look a little bit like A1 is a scalar, and A2 is perhaps a scalar, and well, not here, because we haven't put anything in here to say that this is an array. So this does come a little bit down to personal style choice, personal coding style, but I personally think it's much nicer to always do things like this. So when you're doing even simple array assignments affecting everything in the array, rather than just putting array name equals whatever, 10, 15, whatever we're doing to it, I think it's always best to do this. Or if it's if we're doing it with a multi-dimensional array, do the same. Except of course this is multi-dimensional, so I'm actually missing this. I think it's best to always include something there to indicate what it is that you're assigning to. So here we can see clearly A1 is a rank 2 array, and we're setting everything in it to 0. Without this, it looks to me like A1 is a scalar. So there's no practical difference between the two. This is just much more human readable, and I think potentially going to, because of that, help you prevent bugs from ever happening. So personal choice, I would always include when doing arrays, brackets and just colons inside, just to show that it is actually an array. Okay, any questions about this so far, or are we all happy? Okay, nothing's in the chat, so all good, brilliant. Okay, thank you. Oh yes, I do talk about it just here. Yeah. So yeah, it's always a good idea. It isn't something that's enforced. It's personal choice, but it's probably it's probably going to save you time and maybe a little bit of frustration in the future if you help to prevent bugs that way. Now, elemental intrinsic functions. So we'll actually see later on how we can write our own elemental functions. But something that's helpful to note is that the functions that come packaged within the language itself, and remember there are a lot of mathematical functions provided in the very core of the language. Remember that we've already seen that the behavior of square root changes depending on whether you give it a real number or a complex number. And the same thing happens depending on whether we give it scalars or arrays. So if we give these functions, so here it's cosine is the example that we're using here, an array as an argument, it will work element-wise on everything within the section that we give it. So here we're saying 1 to 4, which is actually everything in the array, but it could be a smaller array section if that's what we wanted. It will work element-wise on those and then pass them back for whatever we're doing. So in this case, we're saying the 4 elements of B are the 4 elements of A, each of them individually going through a cosine operation. Again, this just makes things quick. We don't have to write loops. In some languages, we'd have to write however many nested loops according to the dimensionality of our arrays here, but here we can just do it in a single line and just calculate the function for all the elements of the array that we tell it to, and just flood some other array with those answers. There are other things which we can do. So we can find out the minimum values from arrays, the maximum values from arrays. Here, these are array intrinsics, array literals. Remember, this is with square brackets, how we can create an array literal for assignment. And we can even just quickly sum an array. So it just makes working with them very quick. Again, if you're used to NumPy, this might look a little bit vaguely familiar, and I think a lot of NumPy was based to a degree syntax-wise on the way that Fortran works with arrays. So they might look similar. But if you're coming from C or something, C would require for all of these and to make it much trickier. Yeah, it does feel very similar. The only things to remember, I guess, are that NumPy arrays start at 0. So sometimes that can trip you up if you're trying to, rewrite Python into Fortran or the other way around. So it can sometimes, sometimes just need a little bit of thought. But on the whole, the way that it feels, as you're right, is very, very similar. Yeah, and we can even mask. Again, this is NumPy-ish, if you like. It's very similar. So we can do an array equivalent of if, which is where. We can say where an array is greater than or equal to something is the example here, but we could do whatever we want where an array is negative, where it's exactly equal to 3, whatever we need, then we can do an element-wise operation inside there. The main thing is that whatever operation we do inside the where has to conform with whatever is inside these brackets. So whatever this evaluates to this here is going to be an array operation that evaluates to some array of some rank of logicals of true and false values, and that has to have the same shape as whatever's here, because then we have to be able to do whatever operations we do inside the where block, element by element, only according to where what's in the brackets has evaluated to true. So again, you can imagine if we were doing this and the shape of whatever's in here was bigger or smaller than whatever's here, it just doesn't make any sense. Carrying on. Oh, sorry, I just need to cough for a second. Yes, carrying on. Other helpful functions, again, this can feel a lot like NumPy if you're used to NumPy. We have any, all that work, if you like, a little bit like or and is sort of how they work in the sort of array sense. Any says that if anything at all within the array expression inside it evaluates to true, then any as a whole will come back as true. So here, any a, the entire array A is less than 0, means that if anything at all inside array inside A is negative, then this will come back as true. All, as I say, is a little bit more like and, so this will come back as true only if everything in the entirety of A is negative. And finally, masks, I mentioned a second ago. There are some intrinsic functions. So here we show min and count. and these take optional arguments. So not every intrinsic function has this optional argument, but a lot of them do, where you can just do comma, mask, equals, and then give it an array logical expression to work out. And so this, remember, evaluates to an array of trues and falses, and it will only do the minimum or the count where this is true. So here we find the minimum positive value. Here we again say find all of the positive values inside array and count the number of them. So you can go a long way. You can make, if you like, some very complex array expressions. I didn't write this part here. I like the language used by my colleague who did write it, of array expressions of Baroque complexity. It's a nice turn of phrase, but I do agree it's possible to create some very, very nice, very brief codes with only a few function calls and some reshapes and the like along the way, to make things work in just a line or two of code. But then when either you are coming to read what someone else has written, or someone else is coming to read what you've written, or you're looking at your own code in a year or 2 or 10, it can be sometimes very difficult to understand what's going on there. It can be difficult to understand the code and interpret that. And then the second point here is that if you make these too complex, it can actually become too difficult for the compiler to work out how to take this and how to make it really performative in the machine code for the CPU. And also, I mean, Fortran is considered a high performance language. I mean, we're here working on ARCHER2 at the moment, not exactly in the usual way, I'll say. It's a little bit different to how ARCHER2 is really meant to be used. It's a supercomputing cluster, and we aren't doing any supercomputing at all. But Fortran is used for supercomputing. We will actually talk a little about that at the very end of the course tomorrow. But that means that we want to be able to parallelize our code. And often if we write very complex array expressions, it can be very hard, for the compiler to see how to do that in a performance way, in a serial manner. And it can be very difficult or impossible for us to work out how to write that in such a way that it's parallel. So it could be better to just go with loops. So using these for simple things, using array expressions for simple things is very good. It gives us nice, clean code, but writing nested function calls and reshapes and strange, and unusual or unexpected reformulations of the array in order to get something to work may impede you in the long run. So simple array expressions are best. I've got a question. In serial, is there a difference in computational costs between loops and array? No. So in serial, if you're doing something simple like this, for example, or this, adding numbers to them, or even just doing something like this, using an elemental function, the performance should be the same, because the compiler can just interpret this, because ultimately within the CPU, it has to do one of two things, or a mix of them both. It has to either loop through them, because the CPU would just say one element at a time, do the operation, or if it's able to vectorize, it can take sections of the array from memory and do in a single CPU instruction the entire the operations, every element that it's just taken. Or it can do both of those. But ultimately, it's going to be some mix of loops and vector operations. And whether you were to write a loop in your code itself or do an array operation, the compiler should be able to, it should produce the same machine code, the same assembly. As long as it's something simple like this, as I say. If we had a very long nested set of calls, reshapes, masks, wheres, at that point the compiler might start to get confused and struggle. And at that point, that's where you might actually see a computational cost for using array operations. So that's where we're saying where that boundary is fuzzy, and it probably depends very strongly on what exactly you're asking the compiler to do. But certainly for simple things, things like this is okay. Everything on this page should be okay and should operate, should complete just as performantly as an array operation as it would with a loop. But it's when you start to really nest things within one another that the compiler can get a bit confused. Okay, I hope that answers your question. And we've reached the end of the section. We've got two exercises. I don't actually feel the quadratic equation. I don't feel that this one adds too much to what we've already done, particularly given we were looking at the other example yesterday. I don't think this adds too much. Then we have this other challenge, the sieve of Eratosthenes. I have to really try to pronounce this as well as I can. The sieve of Eratosthenes. So this is a little bit of code to try searching for prime numbers. I think, given we are a little bit behind schedule, spent a lot of time talking about various bits yesterday, I think what we'll do for now is we might leave this and we'll leave it as something to potentially come back to if we feel it could be useful. It's a fairly in-depth exercise, but it's a nice bit of thinking as well. It's a fairly simple but interesting way of finding prime numbers. Yes, so we'll bear it in mind, but I think just now we'll move on. In fact, let's just go straight on. So I think our next section we're actually doing is 12 in our modules. Okay. Yes, so modules. So we have used modules. We used the ISO Fortran env module very early on. Remember, this was an intrinsic module. It came with the compiler. It's defined in the standard, the Fortran standard, which says there has to be ISO Fortran env, and it has to contain these parameters and these functions and so on. It has to provide some defined functionality for the coder. But we can also, and we really should, be writing our own modules as well. So there's a little bit of a look ahead here to what to functions and how they work. We'll be coming onto those in just a bit. But we write a module like so. We begin with the word module, and then we give it a name. We put implicit none again at the very top of the module, and then we can start defining things. So here we define a integer parameter, which is actually a kind. So we use module 1 here to create and store a kind, which we're calling my kind. And then you can put the keyword contains, and then you can start putting functions and subroutines in there. So we haven't yet seen how functions work, but this is just showing you that you can put functions in there and they come after the word contains. Then at the very end, you put end module 1. Again, the name here and the name here has to match. If not, the compiler will be upset and disappointed with you. At that point, though, you can write your main program or anything else that you've written, other subroutines or functions, whatever you need, and they can also be imported with use into whatever you need. And have a question. Can you write more than one module in the same file? Yes, you can. You can put as many modules as you like into the same file. You can put the modules in the same file as your program if you want. But we'll actually cover that in just, I think, very, very shortly. Yes, just below. I'll leave your question because we'll talk about it in just two seconds, and we'll see maybe some advice. But to answer your the actual question is given, yes, you can. Yeah. So formally, again, module name. So a module has to have a name. Remember, a program doesn't have to have a name. You can write a program with just end, but modules have to begin module name, and they have to end with end with the end word. Optionally, you can end with end module name, and I would say that again, this is good practice. This just makes it clear again that the module with this name is now finished. And everything inside it, though, whether you have any specification statements, so this means things like this, creating parameters and the like to store in it. Anything else, any parameters, implicit none, that's all of this. And then contains and any sub programs which go inside. This is entirely up to you, whether you do any or all of these or none of them, whatever. This is up to you writing your code. But module name is required, and it's a good idea to do end module name. Now, as I say, following on from the question which was just asked, can you put everything in the same file? Probably best practice again to help people find code is probably actually to put every module into its own file. So this is where we can start to think about large bits of code. If you're writing a large application, sometimes just finding source code is difficult, and it can help to do this. So what we would recommend is that you put your program in whatever the program's name is. So in your code, you put program, what are we going to call it? Program do CFD, end program do CFD, and then we'd have our do CFD.f90 here. So this would just be named after whatever we've called the program itself. And then we'd have however many modules that we want to use in their own source code files. And again, what we would recommend again is that you give these the same names as the modules that they contain. So up here, we've got module 1. So this would be then inside this file here, where we've given the file the same name, .f90. You don't have to at all. There's nothing to stop you from doing this however you want. But yeah, we would just suggest that for the sake of clarity, you do something like this. How you actually compile those, because then we have to start thinking about how do we compile multiple multiple code units in different files. Well, you can just do ftn module.f90 program.f90. Maybe I can quickly show you that if I go into 08. I think yes. So what you can do is just something like this: module1.f90 program1.f90. That works, and we can then run the program. But what we can also do is we can compile into object files. So we can do ftn-c, and I mean that shows you something else happening. If we do module1.f90, we've now got an extra file here. We've actually got two extra files. I'll talk about this in a second. So module1.o contains module1.f90 compiled into objects. So this is an object file, and this contains compiled assembly, but we can't do anything with it. It doesn't contain actual an actual program to run, and we can see that actually a bit more clearly if we just do this. So if we do this, we get an error because there's a little bit of C poking through. If we run the compiler without any extra options and just the name of some source code file, what it's going to try to do is it's going to try to compile what it's been given into a complete program with a start point and an end point. But module1.f90, if I show you module1.f90, doesn't have a program within it. It just says, here is some reusable code. It doesn't do anything else. There is no start point and no end point. It's just things to be used elsewhere. So that's what this error is saying. It's saying that you can't compile module1.f90 to a program because there isn't a program within it. If we did ftn-c, that's fine because it isn't trying to create a program then. It's just compiling to object files with the expectation that those object files will later be combined to give a full program. The other file that's been created is this module file, and this is a little bit strange. This I think can be a little bit confusing sometimes, and it can be the source of issues on occasion. So at the same time as it compiles this object file, the compiler produces the mod file, and you'll see that it has the same name as the module inside it. So this module1 isn't related to the name of the file, module1.f90, is related to the name of the module within it. So actually, if I quickly change module1.f90, if I change this to module2 and then compile that, oops, I need to change the end as well. So yeah, there we go. So that's what happens if you don't have the same names at the start and end. What we should now have is a module2.mod. So you can see for every module within a file that you compile, you get module name.mod. And this acts a little bit like a sort of header file equivalent. So if you're used to C or C++, this acts a little bit like an automatically generated header file. What's actually in there is completely left up to the compiler. But what the module file does is it provides help to the compiler, because at this point, what the compiler is going to do whenever it tries to use module1 from the object file, I'll just change this back, is let's just say that we're using module1.f90 and module1 within it. At this stage, when we tell the compiler to build something using the module that's being compiled into module1.o, it doesn't know anything about how to use what's in there. So module 1 could contain a lot of parameters, it could contain a lot of functions, and it could contain a lot of subroutines. And all of those could be usable in different ways. And we could put, again, we aren't going to cover it in this course, but you could do object-oriented things as well. So if you create classes for object-oriented programming, you'd put those into your modules. So at this point, module 1.0 could contain all of that compiled to machine code, to assembly. Then in the second step, when we would do program, we would do ftn module 1.0 program 1.f90. Have I done that right? Have I made? Do I need to recompile? I think I need to recompile it. ftn module 1.f90. Yeah, when it comes to reusing it, it doesn't understand exactly how to do so. There we go. That's better. So module 1.0 contains a lot of compiled code. ftn, or well, Fortran, or whatever your compiler is, now needs to know how to use this. And that's where the module comes in. So this contains all of the information that the compiler needs to know on how to actually use the .o file. Exactly what's in here, as I say, is compiler specific. So Fortran, I think Fortran actually, oops, ASCII text. So yeah, sorry, module 1.mod, not. Yes. So Fortran actually just takes the original source code and zips it. So for Fortran, module 1.mod is just a zipped source code file. But other compilers will do things differently. So if I were to switch to Cray, let me just quickly do that. Module load plugin for Cray. What I would now be able to do, if I tried to redo that, this is going to fail. And I'm going to get errors because the module file and possibly the .o as well, if I even just try to, I'm not sure, I'd need a little bit of messing around to get it to work, but the mod files you cannot expect to be usable between different compilers. So the fact, so there are advantages and drawbacks again. Module files are helpful because they're created automatically. We don't need to write header files ourselves. The compiler will generate them for us. That's quite handy. But if we change compilers, we need to make sure that we delete all of the mod files beforehand. So if I rm star.mod and even module 1.0, then I should be able to ftn-c module 1.f90 and then ftn module 1.0 program 1.f90, and that will now work. Or just in a single step, module 1.f90 program 1.f90. Of course, if you're using make files or CMake or Ninja or anything, then you'll be, this will be happening along the way. But sometimes when you're building Fortran code, if you're compiling a large piece of Fortran code and you are reusing files between builds, and then you switch compiler, you just need to do something like a make clean first to make sure that you clear up all of the .mod files. And in fact, yeah, there's this too. See, it's even given it a slightly different name now, module 1.mod. You can sometimes change that behavior. I think, is it EF? I can't remember for the Cray compiler. But yeah, these can be a slight source of sometimes tripping people up. So it's just worthwhile remembering that these are being generated along the way, and that you might need to delete them if you switch between different compilers. And I think that's everything I've just spoken about there. And this is exactly what I've just been doing. So there we go. We've just seen all of this. Yeah. Oh, we didn't try that. Let's just try that. What happens if we do ftn program 1.f90? It complains. What do I do about module 1? Because we haven't told it anything else. The compiler can only work with what we give it. So if we tell it compile program 1, and program 1 is using module 1, which remember isn't an intrinsic, it's going to complain because it doesn't know where module 1 is. It doesn't know how to use it. So we have to make sure that we give everything that the compiler needs to it. Yes, so I think we've gone through all of this then. So scope is worth talking about. So it's sort of slightly brushing up against object-oriented concepts here. So we can choose to make things within our modules public and private, which is how we determine what's visible and what's invisible to anything else which is using this module. So what we've done here is we've just started off our module. This is just the same module as before, but if we put the keyword public in here, inside our specification part, remember this part at the top where we sort of define how the module works, this means that everything within the module is by default public. And that means that anything using module 1 is able to see everything within here that's left at that default. So anything which uses module 1 would be able to see my kind, and it would be able to see function pi my kind. And yes, and something that's important to note is that yes, this is always going to be visible throughout everything else in the module. So what's a little bit different would be to set everything in here by default to private. So we just change that to private here. So implicit's none for everything, private. And this now means that by default, if we use module 1, we wouldn't be able to see anything within here. But what we can then do is we can override that for specific things that we do want to make visible by adding the public attributes to them by hand. So default private, everything is invisible to anything using module 1, but we can override that for integer parameter public my kind. So anything that uses module 1 can now see my kind again. Then we've got my private equals 2. This doesn't have public, so this stays as the default private. Anything using module 1, if we tried to use my private, we would get an error saying I don't know what my private is, because this is held behind a screen from it. It's kept in invisible and private. We then do the same things. This is a little bit different. We have a function. Remember, we had the function pi my kind. The function itself is declared and defined here beneath contains, but up here we can make it public. So we do public : and then give the name of the function. And we can do that for any functions and subroutines. Again, we'll talk about these in just a bit. that you like. So anything public, you just do public : name, comma, name, comma, name, comma, name of anything down here, any sub programs that you want to make public. I have a question. So if a module has a private variable, say potato, I like that, could we also call a variable in the main code potato without causing issues, or is it still best to avoid repeating names? That's a very good question, actually. So remember, we mentioned fairly early on that Fortran doesn't have any concept of name spaces as such. It's just got a single namespace, which is everything visible in the current scope. So if there was something private in the module, and then something in the main code potato, that would be fine. And I don't think there's really any issue in general with doing that. It could become a little confusing, but I would hope at the same time, if you were looking at the module, you should be able to see that it's defined locally within the module scope. It's declared as being private, either because you've given that to it with an override, you'd say private : potato, or it's just private by default. That should be obvious, so there's no issue with doing that. Where there would be an issue would be if you had a public potato. That's a weird thing to say, a public potato. If we had a public potato in our module, and then in our main code or whatever's using the module, we also had a potato, because then we've got two different potatoes, one from the module and our local potato. You could change the name of potato in the module, but that then means you need to change everything that itself uses the module to use something else as well. But what you can do, I might show it if we have a good point to do so. You can use a little arrow pointing operator when you do use module only. You can rename things. You can give local aliases to things inside the module. So we could, within the thing using the module, we could give potato a different name. We could rename it to module potato or potato 2, whatever happens to make sense. And that would then still refer to the one from the module, but within the local scope, it would just have a different name, just so that doesn't clash with the one that we have locally. So it's a little bit of a roundabout. It's not quite as clean as having actual name spaces as some other languages do, but it does work at least. So I hope that answers the question. I don't think you really need to. Yeah, the last part of the question is it still best to avoid repeating names? I don't think so. I think it makes sense sometimes to just use a given name for something, and if you do just want to use the same name somewhere else, at that point I would rename it. I'd give it an alias. Okay, I hope that answers the question. Does that help? Brilliant, thank you. Okay, great. Oh yes, one. Okay, so implicit none. I kept on bashing in yesterday a little bit how important implicit none is. So inside modules, as always, you do want an implicit none. You always want an implicit none, and that should be the first thing that comes in at the very top of the module. When you do that, that cascades down through everything else. It carries on through the whole of the rest of the module, including all of the functions and subroutines in it. So you can write functions and subroutines outside modules, and we'll look at that quickly tomorrow. And if you do that, you would normally put implicit none inside them. Here, when you put them in a module, you don't have to. You can just put implicit none once at the top, and then that carries on through for everything else. Okay, so there's a little bit of a challenge here. So module 1.f90, let's add a private statement and just see what happens. So let's just take a quick look at that. So we'll just make it private, and we'll just see the error that comes up. I've already told you what we expect to happen. We expect to see the compiler complain, and it does. So it compiled module 1, and then when it compiled program 1, it came to kind, my kind, and it said, you've said implicit none, so we can't do implicit typing, and therefore I don't know what my kind is. So that's what's happening there. So that's exactly what we would expect to happen. We've told it it's invisible, and then the compiler just can't see it. So there's a little bit to be said here. I'll go through this just quickly. So I think for a while in modern Fortran, it was fairly common to use modules as a way of passing around global data. So, for example, you could put at the top of a module arrays and things, and this would be quite common. You'd say, let's just put all of our data for a certain structure or the like inside a module, and then we don't have to pass it around through arguments to functions and subroutines. We can just use the module instead. Modern software development actually takes the stance that that's a bad idea, that it's an easy way for bugs to enter code, because it means that changes to your data are almost deterministic. You can be working on an array and then call something with a set of parameters, and then for what is seemingly an unknowable reason, the data in the array has changed. So modern software development kind of says generally global mutables are probably not a good idea. So that's one thing. A little bit more advanced. Don't worry if this doesn't mean too much to you at the moment. It's something you'll probably know about at some point. Is that if you do this, it definitely becomes non-thread safe or re-entrant. And that means that how can I put this? It being non-thread safe means that depending on how things run, if we were to say go into multiple threads or have the function calling itself or in different orders, we would see the data in these arrays changing in non-repeatable perhaps or unexpected ways. It's very dangerous. It means that certainly things like OpenMP for thread parallelism would become very dangerous and probably just not work. And the same thing happens with any variables which are given an initialization. They take on what's called a save attribute, which we haven't covered and won't be covering because again it's not really safe to use. And that becomes basically the equivalent of a static in C, and that's definitely not thread safe or re-entrant either. So again, I'm not going to go too much into detail here, but it definitely means that you're asking for problems if you decide to make this code parallel in any way, or potentially just in normal operations sometimes under certain circumstances. And that's leaving aside this first thing about it. It's this first point about it generally being considered bad program design. So it's perfectly possible to do this, to just have things in your modules which aren't parameters, but instead we would recommend that you don't do that, that you just put parameters at the tops of your modules and nothing else, and that any data, any arrays or any variables, anything at all that is mutable, that is going to move through the program, should just do so via arguments to your functions and subroutines. So no pool of data sat on the side that things can change at will, just a nice flow of data in and out of your various programs. And yeah, we will take a look at this as we go. A little bit of mention of block. I did mention yesterday briefly that one thing that Fortran does that's a little different from, say, C and C++ is that Fortran asks you to declare everything at the top of the code block, of the code unit, actually, I'll say. And only then, once you've done that, do you actually get on with doing your work. Are there any nice examples here? Probably not. If I go back down to 06. Yeah, so here we declare everything, and then we get to work. But sometimes you do want to be able to just introduce a variable for some smaller portion of your code and then forget about it again. And you can do that with the block statement, a block construct. So if you're doing your work, you're doing your maths to do whatever you need to do, you can then do the word block, declare something. So we're creating a new integer at this point. You can declare other things if you want to, and then you can do things using that end block, and then you can get back to other work. So this integer itemp only exists between block and end block. Sometimes you want to do this, so sometimes it can be helpful. I think in Fortran you see this fairly rarely. Generally, people are kind of used to the Fortran style of doing all of your declarations at the beginning, and then get on with work. But if you really want to, this is perfectly possible. There's nothing wrong with doing it. And yeah, if you're used to it, it's a little bit like putting in curly braces in C. Okay, this could be quite nice. Let's maybe just do. I think we have. Do we have a question? No, we haven't got a question. I heard a notification from. Oh no, there is a question. If you allocate an array in a block, is the array deallocated at the end of the block? Do you mean if you declared the allocatable array before and then did the allocation inside? I'm actually not sure. I don't think so. I don't think so. I can check that at lunchtime, perhaps, or in the break, which we're getting towards just now. I don't believe so, Jordan. I'll try and take a look when we have a chance. But I believe that if you were to come down, go into a block, allocate, and then carry on, I think that allocation would persist. It's block is only about the scope of names, so I really don't think that would be the case. But I'll write a quick bit of code in the break or whenever to check. So I'll get back to you on that. But I think the answer is is no. Okay, let's spend just a little bit of time doing this here. So we've got exercise 1. So this, if we take a look at it, is this right? Early episode. Okay, on array. So this was 06, was it? No, 05. So if we go here and take our, so we've got exercise 1.f90. So this is the same code that we were looking at yesterday. So we have the Gauss-Legendre iteration. This is what we were looking at, the very last thing, yesterday. Oh wait, this is asking for a function. This seems like it's out of order to me. Okay, maybe we'll put, I think we'll actually, okay, we won't do this. I will just show you the solution. Yes, that's a bit better, I think, because we haven't actually yet covered how to do functions and subroutines. So I will just show you the solution and ask you to trust that this is how functions and subroutines work. So let's just take a quick look at solution program. So this is meant to be the same code that we did yesterday afternoon, very last thing where we calculated the value of pi. But whereas before, if you remember, that was quite a big bit of code, we've now moved it all into solution module, implicit none. I'm not sure if I've actually said users always come before implicit none. And then we print pi, and then we call a function which we get from the module. And I'll just quickly show you what's inside solution module.f90. So this is what we've just been talking about. We declare the module with the name solution module. Again, we're keeping it the same as the name of the file, solution module.f90. And in that we say everything is public. We create a parameter kp. Remember, we had kp in your code. And then again, we haven't covered how functions work, so I'm just showing this to you and asking you to trust that this is how it works. We say that there's a function called pi Gauss Legendre, and that doesn't take any arguments or anything, but it says n max is 10. We create pi as a kp, and this isn't using the array version of the code. This is just saying these are just scalar reals of kind kp, and it loops and updates pi as it goes, and then calculates pi at the end and returns that. So this is how we return it. We'll see this in a little bit. So we've just moved everything into that module, and then we would just compile it by saying solution module, solution program.f90, and build ./a.out, and there we get the answer. So leaving aside that we haven't written that, I hope you can see how the code that you had yesterday afternoon would be organized in this way. We just put everything into this function, aside from this parameter, because we want this parameter to be usable outside the module as well. We want it to, we could potentially in our program, we can now, if we want, we can create reals here of kind kp now. We can do this. We can say, a kp, because in our module, we've got our integer parameter kp, and we've given it a value, a kind of kind 1.0, and it's public. So both the function and the parameter kp are now visible in the program itself. Will that work when there's an A in the module? Yes, it will. So we're actually going to cover this. This is, again, something that's going to be a bit more helpful once we see the section on sub programs. But this A here, inside the module, this is actually just a local variable inside the function. So Pygauss Legendre has a real KP called A, but this name only exists inside here. So the A inside function Pygauss Legendre is not the same A that we have here. They're in different scopes. So when the compiler is coming through and turning all of this into machine code, it sees here that there's a real that it's going to call A, and that's going to live only here in the inside solution program. And when it's going through solution module and it's compiling the function here, this A is declared, and this only exists within the function. So this is just what scoping is. Unless we make things visible through the top part here, this is where we're making things visible outside I have another question. Isn't declaring the kind publicly in the module like that an example of establishing non-parameter data in the specification module? What if another module did the same but its kind was different? So this is a parameter. So that's the thing. So this is a parameter. It can never be changed. It's essentially just a way of passing constants around. So this is safe. The issue, yeah. So it really does just come down to whether parameter is here or not. With parameter here, this can never change. So it's always safe to use. If parameter weren't here, then anything at all using solution module could change it. You know, so I mean, I may as well just quickly show that. If I delete this, that's now mutable. So now inside solution program, I can say here, do something like kp equals equals 5. This is now going to potentially do something very, very strange. I'm going to try and run this. It might work. It might do something really bad. Oh, it really doesn't like it at all. So it doesn't like KP. Okay, this is good. This is actually a good thing. So the compiler is actually protecting us. But what would be possible if we had, say, other things elsewhere, which we're now relying on KP? We've changed KP. So the issue ultimately comes down to that if we don't protect things with parameter, then we are allowing KP to be changed by other code elsewhere. And because other code elsewhere can just change that whenever it's called, the way that code works can change depending on the order that it's called in, beyond the arguments that we pass things. So if you were to expect a function to calculate pi to always return the value of pi, it would be a bit bad for you if suddenly it started returning a value of 6, purely because somewhere else something had accessed a critical integer or real inside a module and changed it. It sort of breaks it. It can potentially break down cause and effect if you like. It doesn't really, but it makes it look that way, and that's very, very difficult when you're trying to work out where these bugs are coming from. I've actually just at the end of last week was actually dealing with a similar problem happening in some Python codes I've been given to work with, and spent all day trying to work out why something was happening depending on the order that I did some work, and then found that it's because some innocuous function was changing something in a big dictionary that I was using completely unexpectedly. So it's dangerous if you don't have parameter and you start changing things, then the way that the code works can change when you don't think it should do, and it definitely becomes unthread safe. Okay, I think that's us there. Hopefully that's shown you a little bit how that works. We've got some better, I think we have some better exercises coming up, which might be a better chance for people to actually write some code. A very quick thought experiment, and then we'll have a quick break. Can we have the following situation? So here's something to think about. If we have a module A and it uses B, then of course we've got implicit none. And then we do things, end the module. And then if we have a module B which uses A, who thinks that's going to work? Maybe we'll just do a quick poll. Maybe we don't even need a poll. But it can be fun to do. Will these two modules work? Module A and Module B. That's brilliant. I think everyone's coming down on the right side here. Fantastic. That's excellent. Everyone's correct. Okay, great. That's brilliant. Yeah, you're completely right. This isn't going to work because we have a circular dependency. A depends on B, it uses B, and then module B in turn uses A. So A uses B, uses A, uses B, uses A. It goes on forever. There isn't any way out. So you can, if you've ever come across directed acyclic graphs, which are a set of nodes and lines connecting them, and that the lines have directions. This is sort of how we work out how dependencies work. Thing A depends on thing B, which in turn depends on things C and D, and so on. If you want that to be solvable, so working at the bottom up to the top, there can't be any loops. So the compiler has to start at the bottom and work its way up. So it has to be able to do one module first, which is then used by another module, then used by another module. If it's going in circles like this, there isn't any point for it to ever sort of start, and the compiler will probably just not bother. Okay, I think we've reached a decent point there. Let's just take slightly over 12 minutes. It's 11:33 now. Let's just take 10 minutes for a quick break, and then we'll do this section before lunch on functions and subroutines. So let's just pause there, as I say, for just over 10, 11 minutes or so, and we'll come back again at 11:45 at 11:45. Okay, I'll see you in just over 10 minutes. Okay, hi again, everyone. Welcome back. Let's get back to things on our next section, which is, as I kept on mentioning just now, for functions and subroutines. So subprograms. Let me share my screen. Okay, there we go. Okay, so let's get started on this. Functions and subroutines. So we've seen a little bit about functions already, but this follows on nicely from modules, and that we're talking now about how to structure our large code bases, how to make code reusable. Both of these are great things, help us speed up our code writing, keep things sensible, hopefully prevent bugs, well, definitely prevent bugs. So of course, this is what we should be using to keep our code manageable. So coming from other languages, you might be surprised that there are two different types of subprograms. So very often there's only one. That's typically a function. Fortran still uses functions, but it separates functions which don't have return values off into something different, and that's what we call a subroutine. So really, it's just a matter of context. A function returns something. It's best used as part of an expression or an assignment. So my function, open brackets. This will look very familiar to everyone probably. Argument 1, argument 2, more arguments, and that will return a value. So this represents a calculation which then is turned into some return scalar or array, which we can then do something with. And here, what we're doing with it is that we're assigning it into the variable called value. You can't just discard that though. So if my function does something, you really want to be doing something with it when it's returned. A subroutine does something different. So a subroutine doesn't return anything. A subroutine just does work, and it's given arguments just the same. But what we're expecting it to do is to change some of these arguments. So some of them will be input arguments, some of them will be output arguments, and we'll see that we can actually tell Fortran about that, which is very helpful. And you use a subroutine by doing call and then the name of the subroutine. So generally speaking as well, they're typically used, very generally speaking, to do different things, and that functions are typically smaller pieces of work where we just want to calculate some values and which we're then going to do something with. Subroutines are generally bigger chunks of work, more lengthy algorithms, as it says here. There's a little bit of syntax, well, not a little bit of terminology to be aware of here. When we actually call a function or a subroutine, and we provide it with arg1 and arg2 here, these arguments, we call these the actual arguments, in that these are the actual names of real variables or literals or whatever that we're passing to them that are going to be flowing through into the scope of the function or the subroutine to be used there. You'll see that there's a distinction, that there's another kind of argument that we'll be seeing in just a moment, dummy arguments. So just bear in mind that there are actual arguments and dummy arguments. So the number of arguments that a procedure has can be 0 or more. So you don't actually have to tell it to do anything. And I think we actually saw this example here. Function Pygauss Legendre is a function. It doesn't take any arguments at all. So we don't have to put anything into it. We just run it, and it does its bit of calculation, its computation, and it returns the value pi. So you don't have to provide any arguments at all. The ones that do provide it within, the arguments within the definition of the procedure, whether it's a function or a subroutine, are called dummy arguments. And this name dummy means it's referring to the fact that they only have meaning within the procedure itself. So just quickly skipping down a little bit to this bit of code here, subroutine print x. So this is the definition for the subroutine print x. So it says that we have a single dummy argument x, which is going to be a real. We'll talk about the intent in a second. And all that the subroutine does is it prints whatever that value is. The value of x is, and then it prints out x. But this x is the dummy x. It only has meaning inside here. Outside subroutine print x, it doesn't mean anything at all. And that's because we'll be calling print x with anything at all inside the brackets. Perhaps we have something called r, and we want to print that. Perhaps we have a variable called c, and we want to print that. Perhaps we want to provide it with a literal 10, and in which case it will print that. So this is why there's this difference between actual and dummy arguments. The actual arguments are the real, tangible pieces of data that we're passing into a program, and the dummy arguments are just the names that we give them in the procedure, so that we can refer to the same item. Carrying on with the intent, so we can actually do a little bit more, and this is actually very helpful. So this is something new to modern Fortran that I'm a fairly big fan of, because I think this really helps us plan out ahead of time how we want our code to work. It helps us preemptively prevent bugs, essentially. We can work out that the dummy arguments that we're using in our functions and subroutines are going to be in three different cases, three different classes, if you like. Some of them are going to be read only. So this is data coming into the procedure, which isn't ever going to be changed by it. Read-write ones, whose values are going to be defined on entry. So we're going to be taking some data in, but we're also expecting that we're going to change it to update it and then pass it back out to whatever calls us. And then write-only ones, so things coming into the procedure, which could be anything at all. We don't care. All that matters within the context of the procedure, the function, or the subroutine, is that we're going to write something to it. We're going to put some values in there and then pass them back out again. And we can make sure that the compiler is aware of these by adding intent attributes to these dummies. So here, print x, we said that x is only going to be printed out. The only thing that happens to x is that we print it out to the terminal. So we aren't changing it. So we aren't expecting to pass data back out. The only thing we're doing is we're expecting to receive some data in x at the point that we enter the subroutine print x. So let's give it intent in. And this is essentially making it read only. We're saying x is going to be coming in, holding some important data that we do care about, and then later on we're going to do something with it. And we give it intent in, and that's us telling the compiler that if later on something happens within this subroutine which changes x, that's wrong. It shouldn't be happening, and it will raise an error. And that's, again, this is a good thing. If this happens and we get that error, then that's the compiler telling us that we're going against the guidelines we provided to it. We told it that we weren't ever expecting to change x, but now something is changing x, and that's wrong. So this is a very helpful error to get. We'll see a little bit more about that in a second. There's one thing to mention here. If you're particularly coming from C, well, C in particular, I think, you should be aware that Fortran is pass by reference, not pass by value. For some of you, this won't mean very much. For those of you who are coming from a C-like background, this will mean everything, and it may take you a little bit of adaptation. But it means that when we pass a dummy arguments into some procedure, we aren't just passing the value that it contains, we're actually passing the reference in memory to that real variable. So any changes that we make inside here will be reflected outside whatever's calling the procedure to. If we have a function that doubles x and we call it, let's make it a subroutine actually. If we have a subroutine that doubles x and we give it, and at the point of calling it, we give it the variable a, which has a value of 2, and we call the subroutine, and then after the subroutine we print a, we'll see it has a value of 4. So the subroutines do change by default what's coming in here. When we see a dummy name x, we aren't just talking about the value in it, we are talking about the actual variable in memory that is used as the actual argument when we did the call. So that is something to be aware of. If anyone has any issues with that, please do ask questions. Sometimes that trips people up quite a lot. So yeah, please do let me know if you have any questions about this. Other types of intent are possible, and this is where this passing by reference really matters. So let's have another example here. Subroutine increment x. We have intent in out x. So we're going to be taking some value of x in and then making a change to it and then passing the value back out again. So in out basically says care about the value which comes in, but you're allowed to make a change. Intent out says that we're going to be making some changes to it that we want to pass back out again, and we really don't care what the values are at the point of entry. So whatever x is at the point that we enter this subroutine, assign x, the compiler, the runtime do not care at all. The compiler is essentially, if you like, by doing intent out, we're giving the compiler permission to delete perhaps arrays or just completely ignore memory locations, depending on what it thinks is most performant. So by doing intent out, we're saying do whatever it takes, but it's not important at all what x is at the point of entry. So by doing this, it lets the compiler detect any errors that we might make by writing the code, which is very, very, very helpful. It also even provides documentation for the reader, so someone coming through and just reading this subroutine for the first time can quickly get a little bit of a handle on what the subroutines are meant to be doing. And I think there's a question, why can assign x not just have no arguments? Because the point of assign x here is to give the value to x. So we can imagine we have a program that has a real called a again, and we want to use assign x to give it a value. A can be anything at all. It can be 0, 10, minus 10, 10 million, 0.2, whatever. And then we would call assign x, open bracket, a. So we'd give it the actual argument a. And that means that within the subroutine itself, the dummy name x is being used to refer to the actual a that exists in the calling program. And it then gives it the value x, and that's passed back out again. So this is essentially our way here. This single argument is us telling the subroutine where in memory the changes it's making go. So we can tell it assign x a, we can tell it assign x b, we can call it however we like with whichever actual argument here that we like, and every time the subroutine will run and just put the number 1.0 in that actual argument that we give to it. Okay, does that answer the question? Okay, brilliant. Cheers. Okay, great. So yeah, so this isn't necessarily necessary at all. You do not have to provide intents in your code. I would very strongly, very strongly, really recommend that you do. I think it's an excellent way to make you think about the code that you're writing ahead of time. It's brilliant at helping pick up inadvertent bugs that you introduce. I think for very low extra effort, I guess, on our part as the coders, it provides really a lot of payoff. It's very much worth doing. What we haven't mentioned are any local variables. So here, that's all of these, and back in our Pi, Gauss, Legendre code, all of these are local. Well, pi isn't, pi is the return. These are local. So these are variables that only exist as long as we're going through the function, and then they're lost again at the point that we finish. So these aren't dummies. None of these exist here in the brackets. So they aren't dummies. They don't come into the function. They don't leave again. So we don't give them intents. It doesn't make any sense for them to have intents. Intents are purely about the dummies that go in the brackets at the top. So let's try and do this in section 9. Let's attempt to compile module 1 and program 1, check the error message, and sort out the intent. So let's quickly do this. Oops, if I can escape this, and let's go down into section 9. Down again into 9. Here we are. So what was it? Module 1 and program 1. So let's try compiling module 1 and program 1. And we get some errors. Let me actually change to, I think, plugin of GNU. I think that might give us some slightly cleaner. Okay, let's run that. Okay. So I think I mentioned yesterday, it's often when you get multiple errors, always start at the top. This bottom error is saying it can't use module 1. The reason it can't use module 1 is because it couldn't compile module 1, and that was these errors up above. So let's solve the errors in the module. So let's go into module1.f90 and take a look. So first of all, what's going on here? Assign x. So this is a subroutine, a single dummy argument x, and it's saying that whatever x is, we're going to give it a value of 1. Any ideas what that should be? If anyone wants to just type in the chat what intent they think this ought to be. Intent out, exactly. We don't care at all what it was before, because we aren't making any changes to it that depend on its previous state. We're completely ignoring its previous state and just putting the value 1.0 into it. So we can make that intent out very safely. Print x, I think this was fine. Let's just do this. We've got rid of one error. Print x, it wasn't complaining about. This is intent in. So this is saying, let's make it read only and print that out. Let's actually let's actually for the sake of it introduce an error. Let's say that x is equal to x. Oh, let's just make it equal to 1.0. What happens now? It's complained. So this is what I say when it really can help us. We were saying that we didn't want to make any changes. It's actually here, isn't it? We were saying that we didn't want to make any changes at all to x, as we made it intent in, but we're making it different. So it's giving us an error where we've essentially said x should be read only, and then we make a change to it. The compiler tells us that we're making a mistake. So that's where it can really help us prevent bugs. If we've got a long subroutine, it's easy sometimes to forget where you are and make a change to something inadvertently that you hadn't intended to make a change to, and that can really help you prevent that. Increment X is saying intent in. So this is again write protecting it, if you like. Any ideas what this one ought to be? Yep, in out, exactly. Well done. Okay, great. So that should now work, because now we do care about what the previous state was. We do care about what X was before. So that gives us in, but we also want to make a change to it that we can then pass back out again. So we want both in and out. And if we compile that and run, everything is good again. Okay, brilliant. I think we covered everything there. Yes, so remember, you can always come back to these and check on the solutions yourselves if you want to remind yourselves of anything. Functions. So we've seen subroutines. Let's think about functions. These are a little bit different. We say function rather than subroutine at the beginning, but now we have result. So we put the result keyword here, and then in brackets we put the value that we the variable name that we want to be returned by the function. So up above, when we were doing value equals my function, what we do in the result, this is what's going to be passed back out and becomes referred to by the name of the function, essentially. We can still give it whatever dummy arguments we need to. We can still give those intents. What we don't give an intent to is the result, because that's implicitly going to be intent out. So all of the dummies. So you can just simply remember that the only things that you give intents to are the things that come inside the brackets after the procedure name, and that's the same for both functions and subroutines. So here we're saying that whatever intent we want for the dummy, we also do need to give a type to the result. Here we're saying it's just a real, and then inside we do some calculations that result in us assigning a value to A, the result, and whenever we call my mapping, whatever we've put into A here will be whatever is returned under that name. So formally, there are lots more optional things you can do, of course. The prefix, we will actually see a few prefixes. We will see a couple of special types of functions. We'll see recursive, pure, and elementary functions. We've already mentioned elementary functions. But inside, they work exactly the same. A specification part where you declare your variables, give them their intents if they're dummies, and then the executable part where you actually do your computation. There's a little bit of difference here in how slightly older Fortran works. I'm not talking about, ancient Fortran here, but before maybe, I don't know, I want to say perhaps 2010 or something, it was fairly common to see functions declared like this instead, where you would give the function itself a type. So you'd say real function length area, and then inside the executable part of the function, you would just use the function name itself and assign to it. You do still see this. It's definitely not as common at all anymore. More modern code always does it this way instead, using a result. And really, the result should be preferred. It says it allows you to decouple, but it also helps with other things even. So if you want to make your return an array, it's much easier to do it like this, because here you can simply declare A to have a dimension. It's a lot trickier if you want to do it like this. Are functions for, yes, a question. Are functions for returning a single variable, or can they return many? I guess you're thinking of things like returning tuples in Python. I guess that's possibly the thought here. Functions in Fortran return a single item, a single variable. Um, that can be a scalar, or it can be an array. You can, through a little bit of work, have a function return lots of things if you use a user-derived type, which is almost an object. So you can, we will talk about these tomorrow, but user-derived types are a single variable type that you create, which contains subparts, if you like. It contains however many integers or reals with their own names, arrays, whatever you want to put inside there. And you can put that inside the derived types. You can do that. But um, if you're thinking specifically of returning tuples in Fortran, sorry, in Python functions, no, Fortran doesn't do it the same way. So it's returning a single item that can itself be a component of other things, but that at the top level of it being a single item is what really matters. Okay, so it did mention, yes, these different prefixes that you can optionally give to functions. And these can help you, again, make your code clearer. It can help prevent bugs. Sometimes pure can, and it can help the compiler optimize. One such prefix is pure. So a pure prefix doesn't have any side, so a pure procedure, a pure function, doesn't have any side effects, which means it doesn't do anything which affects anything else. So all of its dummy arguments have to be intent in, so it can't change, excuse me, it can't change any dummies. It can't access anything by host associations. That means if you were using your modules in that dangerous way we spoke about earlier, you couldn't make any changes. You can't have anything with save. You can't do any external IO, and you can't put a stop statement. So a stop statement, we haven't mentioned that yet. If you put stop, just the single word stop, as a statement in Fortran, it quits your application. It just stops the code from running. So pure means that your function can't make changes to anything else. It's entirely self-contained. It affects nothing. It just calculates a return value and returns it. So if you have a function that you're intending to work in that way, to make no changes anywhere, just return whatever your return type is, it can be worth making it pure, because then the compiler can perhaps optimize a little. It can maybe inline things. And if you do accidentally start changing something which you shouldn't within the function, the compiler will spot that and raise an error. You can also create recursive procedures in the same way. So you can put the word recursive in front, recursive function. So the Fibonacci sequence is the canonical example, I guess, where you would do whatever inside it, and then you can have the function call itself. If you don't put recursive there, you wouldn't be able to do that. Of course, you might, you can. It's possible to have this work performantly. It's also possible for recursive functions to introduce bad performance because you build up the stack with all of these calls. So maybe sometimes it's better not to. It kind of depends on what you're doing. I tend to avoid recursive if I can, but it's there if you do need it. Subroutines, we haven't looked at them formally yet. They work very similarly, but there's no result because we don't use them in expressions of themselves. We use them in call statements. So remember, a subroutine does a recursive. function only call itself once, otherwise it's an infinite loop, is a question in the chat. A recursive function only calls itself when you call it. So so this example isn't complete. I believe we do have, yes, we do have an example down below. It's perhaps worth doing that. I think that this is worth spending a little time on that. So a recursive function here will only call itself where you tell it to. So at some point in here, you would want to have an if. And that's what we'll be doing in the exercise, where if some condition is met, it doesn't call it doesn't call itself. It just returns something. So there is I think, yes, so we do have return statements here, and this is important. But whenever we want inside a function or a subroutine, we can put return. It doesn't work to return a value like it does in C, for example. It's a little bit different. All that return means is end the procedure here and jump back out to whatever is calling us. So that's what we would be doing here. Inside here, to make sure that we aren't just calling Fibonacci forever and ever, we would do something. We would have if some condition, then result nf equals something return. So that's what we'll see in the example. Okay, and yes, modern code styling, code thought again is that it's a good idea in Fortran to, rather than place your procedures by themselves, which you can do if you want, it's actually better to put them inside your modules. And that can mean just writing modules which do nothing but contain procedures. There are reasons for this, which we will touch on tomorrow. There's something called an interface block. It generates what we call the contract block. So when we want a calling procedure, so the program itself or another subroutine or function to call some subroutine or function of our own, by putting them in the module, they go into the .mod file. And that's what I meant earlier when I said that that means that the compiler is always able to look that up and understand exactly how it should be using those functions and subroutines. Without that, the compiler has to make a guess. It has to actually trust you. And if you've done something wrong, that can be a source of bugs again. Sometimes that's also required if we're doing things like passing allocatable arrays, because they don't actually exist in the memory until they've been allocated. That can be really difficult for the compiler to understand unless we put it in a module. There's a question: is procedures the collective term for functions and subroutines? Yes. Yeah. We go back and forth. We call them procedures. We call them programs. Both of those are fine. It's just a way of collectively talking about both functions and subroutines, because they're almost the same thing in terms of what they're intended to bring to us, what they're intended to enable for us. They're the same. They're just slightly different contexts for doing the same thing. So rather than just always say functions and subroutines, we just say procedures instead, just to make it a little bit quicker. Okay, great. So it's it's 12 just now. So I think what we might do is we might spend this is going to be a little bit more than this. Let's see if we can maybe do this for the next 10 minutes. I'll actually let you get along with this. So I would start, if you like, from the template. So this is the solution to the pi calculation that we did yesterday and earlier on. but there's a solution given here in exercise program 1 and exercise module 1.f90. We can take a look in that quickly. Exercise, let's take a look in the program first. It uses the module, implicit none, and then just calls pi Gauss Legendre. And if we then take a look at exercise module, we've got 3 things to do. One is to see can this function be declared pure? And then we've got 2 more things to do to write of our own. So we've actually got some code to write here. Add a subroutine pi Gauss Legendre. So basically taking this function and rewriting it as a subroutine instead. So we've got both both a function and a subroutine that do the same thing. So you just call them in slightly different ways. Then a little bit trickier, add a recursive function Fibonacci n to return the nth Fibonacci number for n greater than or equal to 1. So here, what you want to do, you want to start from this up above, take this as your starting point, copy and paste this in at the very bottom. So I'll just actually show that. So let's just put this in here. I'll just make it look a little bit better. And now what you've got to do when you do this is to work out what goes in here. So let's just start working on that now until 1:30, and then I think we'll take our lunch until maybe 1:30. We'll maybe take an hour's break for lunch. But I think doing this just now would be a very good idea. I think this will be a nice test of just making sure that we understand how functions and subroutines work inside modules. So I'll start this off with you all. So if you remember, the first thing we had to do was just to take a look at the function that calculates pi and check, does it work as a pure function? Oh, I've got something open over here. Let me check this quickly. Not that. Okay, doesn't matter. Okay, so the first thing that we're doing is checking that first function, can it be made pure? So let's just take a look at it. Remember, the various conditions are that we don't want to have any dummies that are anything other than intent in. We can see, first of all, that that's perfectly fine, if only because there aren't actually any dummy arguments at all. So we don't even have any to check. So that's okay. Do we make any changes through use association? We don't use any modules, so we don't make any changes there. We really shouldn't be doing that anyway. Thankfully, we aren't. Are we doing any input-output to file? Nope, we aren't making any input-output to file. There was another condition which, have I lost it? I just can't scroll. No stop, exactly. No stop, thank you for reminding me. Yep, we don't have any stop either. So that looks good, doesn't it? So we should be able to make that pure. So we just add the word pure in front of function. Let's save and compile that. I'm doing the wrong one. FTN exercise module 1 and exercise program 1. NF has no implicit type. What have I done here? NF. Oh. It's because I put this in. Let me just comment this out quickly. Yeah, that was me getting a little bit ahead of myself. Okay, so that's out of the way again. Let's recompile that. And that seems to work fine. So we were able to turn that into a pure function without any issues. Let's now think about doing this as a subroutine. So let's try to, I'll just be a little bit a little bit naughty, I'll just skip typing it out by hand, and I'll copy and paste it in. So I've just copied and pasted the function. Let's just give it, let's just try and change this into a subroutine. So we don't want it to be a pure function or a function at all. Let's just make it a subroutine, pi Gauss Legendre. And it's only going to do one thing. Remember, there are no results for subroutines. We just have input and output dummy arguments. So let's change it at the end here too. Let's change this to subroutine. And then we probably will also want to change the name. Let's just call it pi Gauss Legendre sub for the sake of it. So pi Gauss Legendre sub. So we've got the function and the subroutine. So that's that. There's really only one other thing here that we want to do. Any ideas from anyone in the chat? What might be needed to just make this a little bit better? Intent, exactly. We've got a dummy argument now. Victoria's asked, can you have functions and subroutines with the same name? Yes, you can, but it might need a little bit of work. So we aren't actually going to talk about that just now. We'll keep it simple for now. We'll talk a little bit about that tomorrow morning, I think it is. Is it tomorrow afternoon? Tomorrow morning, I think. We'll touch a little bit on that. At that point, we're starting to talk about overloading things. So we'll just leave that to a slightly more advanced spot in the course, but yes, in general, yes. Okay, so the last thing that we want to do is to add an intent. So let's just make it intent out, because we don't care at all. Brilliant, thanks, Victoria. Yeah, we don't care at all what pi is beforehand. We're calculating it fresh, if you like. We're calculating it from scratch here, and then passing whatever value we put in the dummy pi back out again to the calling program. So let's just check that this works. Let's see if we can get our exercise program to use it. So just to emphasize actually something, so let's make a real KP. So we've got KP from the module. So we're able to use that through use association. And let's just give it a different name. Let's call it pi sub. And so I just want to emphasize something here. Pi sub equal, no, so I'm doing that wrong. It's a subroutine. So call pi Gauss Legendre. And the argument that we're giving it, so the actual argument, pi sub, print star, pi from sub, and then we'll just do pi sub. Let's make sure that that compiles and runs. Pi Gauss, oh, I gave it the wrong name. Pi Gauss Legendre sub, of course. Let's recompile. Okay, that's good, and run, and that works perfectly. So I just wanted to do one thing there, just to emphasize something. So I called the actual argument pi sub, and pi sub is real of kind KP. But inside the module, exercise module .f90, I used the dummy argument pi. So this, I really just want to make sure that people understand this. The dummy argument that we give here inside the definition for the procedure, whether it's a function or a subroutine, doesn't matter, is entirely local. So this is just a local name that we're giving that only matters here inside the procedure for whatever we are putting in brackets outside when we call it. So outside we had a real, which was a real KP, but we called it pi sub. So that's the actual argument. In here, we're just saying whatever we can do this, we can call a program we could call, let's have another one. We could have another pi, and then we can also do call pi Gauss Legendre sub, and we could call it with another pi. And inside the subroutine, it's referring to both of those with the local dummy name of just pi, but here the actual arguments are two different real KPs, pi sub and another pi. We can reuse the code over and over again, providing different actual arguments. And because we're passing by reference, which is a specifically Fortran thing, we are really passing through the locations in memory of both of these variables for the subroutine to modify and then pass back to us. So I hope that makes that just that tiny little bit of subtlety a little bit clearer, because depending on what language people are coming from, that may not have been obvious. I hope that makes it clear. So I will leave things there. There's still this last bit. We are now at 1:30. So what I'll say we'll do is I'll leave this for now. We can go away and have our lunch, and I'll probably just have a sandwich while I'm sat here in front of the keyboard. But I'll put this in myself, and any one of you who want to have a go at writing this recursive function on your own, please do go ahead and have a try. I think that'd be really helpful to just make sure that you're able to do this. And then after lunch, we'll just spend 5 or 10 minutes going over what I've done. And if anyone's had any issues in their own attempts, we can talk about it then and make sure that everyone is on the same page. But other than that, yeah, let's leave it there for just, yeah, let's just say we'll have an hour's break, a decent break. And we'll come back to this after we've eaten and had a little bit of a rest. And then we'll also talk about some IO and formatting and the like this afternoon. That's a little bit simpler, at least. But okay, we'll leave it for there. I'll see you back here again at 1:30. What I might do, I will actually, sorry, coming back, I'll put a couple of hints in here, just in case anyone wants to start doing it. So I'll just put a couple of small hints in my code, and I'll leave that on screen for a moment, and hopefully you can follow that through yourselves. Okay, see you in an hour.